Hey everyone, welcome back to Abstract Algebra 1. This will be lecture 11 of the course. And in this section, we're going to explore a very interesting area of group theory, and that's going to be the topic of normal subgroups and factor groups. So let's go ahead and get started. We're going to call this section 2.9, and that's going to be normal subgroups and factor groups. Okay, and so we saw previously that if G is some group and H is one of its subgroups, then it's not always true that the left and right cosets will be equal. So we saw previously that for H, a subgroup of G, it is not always true that AH is equal to HA. Right? We saw that this may or may not be true. So it's not always true. Now, there are some cases where this turns out to be true, and it's those cases that we're going to be interested in this section. Right? It's those cases that it turns out, I mean, this may be something that you maybe would have glossed over and be like, well, it just doesn't always work. Turns out that when it does work, it leads to a very interesting area of group theory. And that's what we're going to be concerning ourselves with tonight, when this works out. So we will be concerning ourselves with cases where AH equals HA for all A and G. Okay. And so to start that investigation, we need to talk about what is called a normal subgroup. And so we'll start with that definition. Okay, so a subgroup H of a group G is called a normal subgroup of G. It's called a normal subgroup of G if AH equals HA for all A and G. Okay, right? And so notice it says for all A and G, right? So it doesn't say for all H and H or any of that. It says for all A and G, A times A, the left coset of H built on A, is equal to the right coset of H built on A. So it's for all A and G. That's critically important. We'll break that apart in a second. But typically we denote this normal subgroup relationship. We denote it by H subgroup of G, but we add this one little thing here. We put maybe a little sideways triangle here, right? So this means that H is a normal subgroup of G. Okay. So something to note, and we just kind of touched on it, but it's a common mistake to think. So it is common to think that H being a normal subgroup of G means that AH equals HA for all A and G. It does mean that, and for all H in H. Right? It doesn't mean this. This is not true. This is not the meaning, right? So you have to be careful of the way the definition is stated. A subgroup H of a group G is called a normal subgroup of G if AH equals HA for all A and G, right? So what that basically means is that for A and G and H in H, there's going to exist an H prime and maybe an H double prime in H, such that AH equals H prime A and H times A equals A times H prime, right? So look carefully at the notation, this is not little h, it's big H. So this is denoting the subset H, right? Well, I'm sorry, in this case, the subgroup, right? H is a subgroup. It's not an element. It's not a specific element, right? And so all we need is for a specified A and a specified H, we need there to be some other element in H for which this relationship holds. And same thing over here. For a specified H and a specified A, we need there to be some H prime such that this relationship holds. Okay, so you can switch the order of the product of an element from the group and the normal subgroup, but you'll have to fudge the element from the normal subgroup, right? So you'll have to fudge here H using H prime or H double prime. And the H may be equal to H prime or H double prime, but it may not be. Right? So that's the thing to keep in mind. It doesn't necessarily mean explicitly AH equals HA for all A in G and for all H in H. It is not this. It could be in some very specific cases, but in general, it may not be. Okay? All right. Okay, so that's the definition of a normal subgroup. That's what we mean by a normal subgroup. So this is the definition. And you can see obviously that the idea of a normal subgroup is tied intimately to the concept of a coset. Right? And so we'll be using the coset theory, coset ideas throughout this whole section. Okay, so let's start by the identification of a normal subgroup. So we know the definition, but how do we tell if a subgroup that we're looking at is normal? Like without exhaustively checking every element, right? So how do we tell that a given subgroup is normal? Well, the best way to do it usually is to use this theorem called the normal subgroup test. And this is usually the way we want to check these things. And so what does it say? It says a subgroup H of G, is normal in G. It's normal in G if and only if X inverse is in H for all X in G. Okay, so if you're interested in determining whether or not H is a subgroup, a normal subgroup, then you need to check this condition. Okay, you need to check this condition. All right, let's prove this theorem. Okay, so we'll start by assuming that H is a normal subgroup of G. Right? So we'll assume that H is a normal subgroup of G. Then for any X in G, and H in H, there exists H prime and H double prime in H. Well, actually, we don't need the double prime yet. Let's go with this. There exists H prime in H such that XH equals H prime X. Okay, and then from this we can just do a little bit of algebra, and we get XH X inverse equals H prime. And so that implies, of course, that H prime is obviously in H, and so therefore XH X inverse must be, sorry, this is a whole group, sorry, must be in H as well. Okay, right, and so that gets us the forward direction. Okay, what about the other direction? Okay, so conversely, we want to next assume that XH X inverse is a subset of H. Okay, and this would be true for all X. Okay, Then let's let x equal a. Okay. And we have, what do we have? Well, AH, A inverse is a subset of H. Okay. Or also AH is a subset of HA. Okay. And on the other hand, right, so that's one direction. On the other hand, right, letting x equal A inverse, we get the reverse inclusion, right? So we get A inverse H, A inverse inverse, which of course is A inverse H, A. That's obviously a subset of H, right? Or you would say HA is a subset of AH, right? And so obviously they're the same. Okay, and so that's the proof. So that gets you exactly what you need. All right, and so that's the normal subgroup test. And so this is going to be probably the most expedient means by which to confirm that a subgroup is indeed normal, right? So just check for this condition. We'll see some examples where we check for this. Okay. Let's talk a little more about these subgroups through some examples, in fact. Okay, let's take an example. Now, we've seen some special subgroups already, some special groups. Let's think about an abelian group. Turns out that every subgroup of an abelian group is normal. Okay, I mean, what is an abelian group? An abelian group is a group where AH equals HA for all A and H and G. Right? So it doesn't really matter if the H happens to be in a subgroup and the A is not necessarily in the subgroup. Right? You still get the same results. So it doesn't really matter if the H is in some subgroup H. Right? You get it. You get it automatically, right? In an abelian group. So that's one example of a broad category that we've seen, which definitely fits this definition of normal. So every subgroup of an abelian group is normal. Another example where we've seen so far is the concept of the center of a group. So the center, and remember we denoted that ZG, the center of a group, G, is always normal. Now let's recall what the center is. Right? The center is all of the x in the group such that xy equals yx, and that's going to be for all y and g. Right? So basically the center of a group is the collection of elements that commutes with every element in the group. Now, we've seen this in the case where we've seen examples where you've got some elements that happen to commute with other elements. Always the identity, for example, commutes with every element. Sometimes there are more elements in addition to the identity that commute with everything, and that collection of elements that has that property is what we mean by the center. Right? So the center of a group is always normal as well, and really for the same reasons. By definition, it commutes with everything, so it doesn't matter if one of the elements happens to be inside of a subgroup, right? So it's obviously going to work still. Okay, so these are kind of easier examples, but good examples still. Good examples, right? These are just kind of pulling together like some common notions, and just, in doing that, you should hopefully be able to develop some intuition about what this concept of a normal subgroup is, right? So it's an abelian group, every subgroup is normal, and the center subgroup is also normal automatically. Okay, here's a little less, well, this one's also kind of It's relatively straightforward. This is the alternating group. So the alternating group, AN, right, of even permutations is a normal subgroup of the symmetric group, Sn, of all permutations. Okay. Right, so we can see an example of that. Let's consider a couple elements here. So the permutation 1, 2 is in Sn. It's odd. It's an odd permutation. And the permutation 1, 2, 3 is in An. It's an even permutation. Now remember this idea of odd and even, right? What does that mean? Remember what that means. Even means there's an even number of 2 cycles that can be used to represent the permutation. Odd means that every product of 2 cycles, there's an odd number, right? So here this is odd because 1, 2 can only be represented as 1, 2. There's no other way to write it. 1, 2, 3, remember that can be written as 1, 3, 1, 2. So it's a product of two cycles, i.e. 2 is even. Right here you've got 1, 2, 1 is odd. So that's the difference between odd and even, right? So the alternating group is the set of all even permutations. So it's a set of all permutations like this. And so in this case, you've got, you can think of like your AH equals HA. That's what we're interested in, H prime A, we'll say. And so in this case, you've got your, like your 1, 2 is your A, and your 1, 2, 3 is your H. Okay. Now, what is 1, 2, 1, 2, 3? If I kind of reduce that, what does that boil down to? Well, if I start with 1, 1 comes in, it goes to 2, and 2 goes back to 1, so it's closed there. And then 2 comes in, it goes to 3, 3 comes in, it goes back to 1, and which goes back to 2. Right? So that's what A times H looks like in this setting. Now, if I try to set that equal to 1, 2, 3, 1, 2, what do I get here? Well, let's see here. 1 comes in, it goes to 2, which goes to 3, and then 3 comes in, it goes back to 1, so it closes there, and then the 2 comes in, it goes to 1, which goes back to 2, so it closes. Now, these are not equal. Right? So in this case, these are not equal. But remember, H doesn't have to equal H prime. It doesn't have to equal H prime. It may, but it may not. Is there a different H prime that we could select from the alternating group? There is. One that will make this work? Yeah. So instead, let's do this. There's your A and your H. 1, 2 is your A. 1, 2, 3 is your H. Now remember, 1, 2 is from Sn, right? That's all permutations. And 1, 2, 3 is from An, the set of even permutations. So remember, An is playing the role of H, Sn is playing the role of all your master group. Okay. It turns out that there's another permutation that we could use, and that's 1, 3, 2. That's also an odd or an even permutation. So it could be your H prime, and then your 1, 2 would be your A. Now these are equal, right? So 1 comes in, it goes to 2, 2 goes back to 1. 2 comes in, it goes to 3, 3 comes in, it goes back to 1. Okay, do we get the same answer over here? So 1 comes in, it goes to 2, it goes back to 1, so it closes that up. 2 comes in, it goes to 1, goes to 3. 3 comes in, it goes back to 2, closes it up. So they're equal. So in this case, this is the scenario. So in this example, H is not equal to H prime, since 1, 2, 3 is not the same as 1, 3, 2. But both of them are in H, which in this case is the alternating group of even permutations. Okay, so it still works, right? So it turns out that AN is a normal subgroup of SN. So you can think of this as all perms, and this is even perms. Okay, so that's another example. All right, let's take a look at another example. Let's pull out our dihedral group. Okay, this is D4. So D4, remember D4 was the rotations R0, R90, R180, R270, and then the flips. So you had a horizontal flip, a vertical flip, and 2 diagonal flips. All right, remember these are from maybe the 3rd lecture in the series where we were talking about symmetries of the square. So recall symmetries of the square. All right, this is a great group to use for examples. It's very highly structured. It's also physically intuitive, right? It's built up on a physical notion that once you go through it, you can kind of rely on it for a lot of things. Now it turns out that there's the rotations. I'm going to call it R. So R0, R90, R180, and R270. This is a normal subgroup in D4. So R is normal in D4. Right, and so what that means is that AH equals H prime A for all A in D4. Okay. So let's take an example here. Right, so let's see here. Let's let A equal D, the diagonal flip, the main diagonal flip, which is an element of D4. And I'm just trying to translate the AH notation into like actual elements from D4 here. And let's let RH equal R90, which is an element of this subgroup R of the rotations in general. Okay, and so let's kind of break this down using these two specific elements. So AH in this case would be D composed of R90. So D composed of R90. Okay. And so let's see what this looks like. So if I start with my 1, 2, 3, 4, let's just actually derive this from first principles here. If I apply an R90 to this, then I get 2, 4, 1, 3. And if I apply a D to that, I get 2, 3, and then 4, 1. The diagonals flip, right? And so I get this, right? And so AH equals D R90 would be equal to 2, 1, 4, 3, right? Which would be, in this case, it's also equal to R90 inverse D. Right, so let's look at that. How is that? Is that actually true? Well, let's start from scratch here. 1, 2, 3, 4. And let's apply a D to that first. When I do a D, I get 1, 3, 2, 4. Right, 1, 4. The diagonal flips. Right, and if I apply an R90 inverse, what is R90 inverse? That's R270, isn't it? Same deal. All right, remember this guy here is actually R270. And so when I do that, what do I get? Well, I'm going to rotate everything 270. So my 3 comes down here, my 4 goes there, and then my 1 is here, and my 2 is there, right? So these are the same. Okay, and so AH equals DR90, which is equal to, and we just showed, R90 inverse D, which is equal to R270 D, which is H. Turns out H prime would actually in this case be H inverse A. right? So this is just a specific example. Here H prime turns out to be the inverse of H. That's not necessarily going to be the case every time, but it turns out to be the case this time. Right, so here's an example. Here's an example, right? And so this tells you that in general, R is normal in D4. The rotations are normal in D4. And here's an example of how you can go through and confirm it for a pair of elements. Right, now, this is not the way to test it exhaustively. You'd want to use the theorem, but this just shows you the mechanism. What it really means for it to be normal is that this kind of relationship holds for all the elements of D4, all of the A in D4. Okay, that's a great example. I like that example. We'll come back to the dihedral group as a kind of walk through a really critical example in a second. Okay, another example. The group. Here we're going to pull in the matrices again. So SL2R. This is the 2 by 2 matrices with determinant 1. Right? So SL2R is a normal subgroup. It's a normal subgroup of GL2R. Now remember, those are 2 by 2s with determinant not equal to 0, non-zero determinant. Okay, now how can we verify this? Well, we certainly don't want to try anything exhaustive. These are both groups with infinite order, so there's no way we're going to exhaustively check anything here. We're going to use the normal subgroup test. So to verify, let's let X be an element in GL2R, right? And so this is like your group, right? So let's clear that up. So there's your subgroup, and this is your group, right? H is the supposed subgroup, G is the group itself. So we're going to let X be a member of the group, and we're going to let H be an element in SL2R, which is our candidate normal subgroup. And we're going to notice something, that the determinant of X, H, X inverse, right? So I've just taken some random matrix out of here and some random matrix out of here, and I'm just going to throw these in here and see what I can see. Well, that determinant, what is that determinant? Well, it's equal to, because these all have non-zero determinants, you can break this apart. So it's the determinant of X times the determinant of H, and then it's going to be the determinant of X inverse, but if you recall, the inverse of the matrix is the reciprocal of the determinant, so you can do this. And so this middle guy here is 1, right? Because H is in SL2R, which has a determinant of 1, and so this is equal to the determinant of X times the determinant of X, that number's inverse. And so of course, if this is like 2, then this is 1/2. If this is 27, this is 1 over 27, right? And so this is equal to 1, that product. And so what does that tell you? Well, that tells you that XHX inverse is itself in SL2R because it has a determinant of 1, which is of course your subgroup, right? And so that means, therefore, XHX inverse is a subset of H. That's the condition we need to see in order for the subgroup to be deemed normal. Okay, and so we can see here that SL2R is a normal subgroup of GL2R. Fascinating. Excellent, right? Okay. I love it when we introduce a new concept and then we can revisit some of these examples that we've been working with and we see, oh, this new concept applies to these familiar examples. Okay. All right, so that's normal subgroups. Now, what's the big deal? Well, I mean, you might be thinking to yourself, okay, it is interesting that some of these examples have this characteristic, but why? What is the very special significance, right, of that we spoke of at the onset here? So what is the special significance of H being a normal subgroup of G? Right? What makes it so special? Well, when you have H be as a normal subgroup of G, then what it basically means is that the set of left cosets of H is itself a group. Okay. When H is a normal subgroup of G, then the set of, I'll just say left cosets, but it applies to left or right cosets. The set of left cosets of H and G is actually a group itself. Okay, it's itself a group, and that group has a very special name, and we'll define this in a moment. But I'm going to lead with the punchline here. So when you have H as a normal subgroup of G, then the set of left cosets of H is itself a group, and that group is called the factor group of H. Right, factor group of G in H, by H. Yikes. Okay, so the factor group of G by H. In H, yeah, I mean, it's not wrong to say it's the factor group. Well, it would be wrong to say it's the factor group of H. It's the factor group of G, right? H is how it's set up. Another, you'll also you'll hear these called. Also, these are called, well, they're referred to as quotient groups. We'll see why in a moment. Quotient groups, again, of G by H. Okay, and so what the heck is a factor group or a quotient group? Well, it's the set again of left cosets of H, right? So let's generate a theorem here. We'll start from a theorem, and we'll see what this thing's all about here. Let's let G be a group. Let G be a group and H a normal subgroup. H a normal subgroup of G. Okay. Then the set, right, this is the notation, the set G, and sometimes it's the terminology here is G mod H. You could say it like that, or G divided by H, or G of H, or G by H, I think is common as well. So G mod H is equal to A H such that A is in G. Okay, so the set G mod H is a group under the operation. What is the operation? Under the operation, okay, the operation is AH, if I have an element AH in this G mod H group, and another element BH, and I compose them like this, then that's equal to ABH. Okay, this is the operation of this factor group. Right, so this is what we mean by the factor group. Or the quotient group. Okay, and the fact that it's a group is not obvious. We're going to prove that it's a group here. Right, we have to prove it. But this is the idea. Right? And so the way to kind of think about this is that G mod H is really just the set of all left cosets of H. Okay? It's the set of all left cosets of H in G. Okay? Okay, it's not a single coset and all of the elements of the group. It's actually the set of all cosets, and the cosets are the elements themselves. Right? So the cosets are the elements in G mod H. Okay. Key idea. All right, let's prove that this is a group. Okay. So we wish to show that G mod H equal to AH such that A is in G is a group, right? So usually there's only 3 things to show. In this case, there's actually 4. So we need to first show that this operation is new and kind of different. So we need to show that it's actually a function. We have to show that. Then we're going to need to show identities and inverses. And then, of course, the last thing, or maybe the first thing, operation-wise to show is associativity. And once we have all of those things, then we'll be able to say, oh, yes, indeed, this is a group. Okay. So we'll start with item 1. We'll show, let's just concern ourselves with this this operation and make sure that it actually makes sense, it's well defined. Okay, so 1. So what's the correspondence that's given? So the correspondence is that you've got G mod H cross G mod H into G mod H. Right? Is this actually a function? Right, so let's assume that AH equals A prime H and BH equals B prime H, right? H is a normal subgroup. This ought to work, right? And so then A prime equals AH1 and B prime equals BH2, and this is going to be for some H1, H2, and H, right? Right, and so just kind of starting point here. All right, so this is our starting point. What do we have? Well, A prime, B prime H, right, is equal to A H1, B H2, H. Okay. Okay, and so that's equal to, what are we going to do? Well, we're going to, let's lose the parentheses because we're going to be using some associativity here, right? And so H2H becomes just H. Why is that? This is property 2 from a couple of sections ago. Right? This is, if you look back a few lectures, and basically what it said is that AH equals H if and only if A is in H. Well, obviously H2 is in H, and so H2H is just H. Okay. All right, so kind of moving forward here. We can swap the B and the H. AH1, HB. Now, why can we do that? Why do these flip? Well, it's because it's a normal group, right? This is the normal subgroup. That's what it means to be a normal subgroup, right? BH equals HB. Okay, so we can flip those around, and then we can absorb the H1 again. Right, and we get this. Right, and then of course we can switch it back around again and we get that. Okay, so we've just shown that A prime B prime H equals AB H. Okay, that's exactly what we needed to show, right? We've drawn from here down to here. Okay, and so that tells us that this function, this operation is well defined. We don't have to worry about the operation. It works. Let's move to 2. What about the identity? What is the identity in G mod H? Oops, let's stay consistent. There we go. What is the identity? Well, it's just EH, isn't it? Right, EH equals H. E is certainly in the subgroup H, so it's just H. Right, so EH is the identity. What about inverses? What are the inverses here? Well, if you have AH, A inverse H is the inverse. Okay. Right, and that's easy enough to see. A inverse H times AH, according to the operation, is A inverse AH, which of course is just H, the identity. Okay. All right. And then what about associativity? What about associativity? Well, the way to do it is just start with an AH and a BH, like so. Oh, sorry. Okay, so you've got AH, BH, CH. We'll associate it like this. Well, this is equal to AB, H, CH. Okay. And that's equal to ABC, H, which is equal to AH, BC, H, which of course you can expand that out again, and that's equal to AH, BH, CH. And so that's associativity. Okay, and so here again we use that property 2. Sorry, not property 2. We use the fact that we're dealing with a normal subgroup to swap the C and the H here. Okay, so that in there is the normal subgroup being used, right? And then these are just elements of the group, so you can combine them. Group is obviously associative since it's a group, right? And so you can just end up with this nice associativity argument. And that's it. So those are the properties that are required in order for a group to be a group. And so GH is therefore a group. G mod H is therefore a group. Okay. Right, so that's pretty interesting. Now you may be thinking to yourself, I don't understand what I'm looking at here with this G mod H business. Let's do some examples. Got a bunch of great examples here that will help you to develop some good intuition on this. Start with something simple. Let's let 4z equal this set: 0 plus or minus 4 plus or minus 8 ... Okay, yeah, I mean, if you like to look at it this way, another way to denote this, of course, would be using this -8, -4, 0, 4, 8, right? So whichever way you want to think about it. Okay, so let's call 4z that. And we're going to use, so this is obviously a subgroup of the integers. Okay, if I add 4 or I add 8, then I'm going to get another number in here, right? This is a subgroup. So 4z is a subgroup of z. Okay. Now it turns out that 4z is actually a normal subgroup of z, so it's stronger. So 4z is a normal subgroup of z. Right? You can go through and confirm that using the proof, but let's just take it for granted in the interest of getting through the example. So 4z is a normal subgroup of the integers. Okay. Now let's talk about if we want to construct z mod 4z. To construct this, we need to know what the left cosets of 4z are. Right? And this is a super easy group to work with. So you can start by just saying 0 plus 4z. Well, that's just 4z, right? That's equal to negative 8, dot, negative 8, negative 4, 0, 4, 8, dot, dot, dot. Okay, so that's obviously easy. That's the subgroup itself. What about 1 plus 4z? Well, that's going to be dot, 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 negative 11, negative 7, negative 3, and then 1, 5, 9. Okay, so this is another coset. Another coset would be 2 plus 4z. So dot, 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 and then we'll say negative 10, 6, negative 2, positive 2, 6, and 10. Right, these are infinite, sorry. I should put the dot, dot, dots there. And then 3 plus 4z. That's going to be your negative 9, negative 5, negative 1, 3, 7, 11, dot, dot, dot. Right, so now notice here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So everything in Z is in one of these 4 cosets. And notice that none of them intersect. There's no intersection. So these are the 4 elements of the factor group. These are the 4 elements of the factor group, and this is the factor group Z mod 4Z. Right, so you've got 0 plus 4Z, 1 plus 4Z, 2 plus 4Z, and 3 plus 4Z. So these are the four elements of the factor group Z4Z. Okay. Now, so this is a group. Let's look at the Cayley table, the multiplication table, or the operation table. We'll call it a Cayley table. Right. Remember what the Cayley table does is it takes all the elements and it shows what the result of the operation is on the elements. So to build one, you start by 0 plus, you list all the elements, 0 plus 4z, 1 plus 4z, 2 plus 4z, 3 plus 4z, right? You do the same thing across the top. Like so. Right? And then you just ask yourself, what do these things, what happens? What is the operation? Well, obviously, 0 plus 4z plus 0 plus 4z is 0 plus 4z. This is 1 plus 4z, 2 plus 4z, 3 plus 4z. That's straightforward. What happens when I combine 1 plus 4z and 0 plus 4z? Well, 0 plus 1 is 1. Right? And then I get 2 plus 4z here, 3 plus 4z there, and then 1 plus 3 is 4, which is the same as 0 plus 4z. Okay. And then 2 plus 0, so you can see how this fills out. Sorry, that should be 0. 0 plus 4z. It is 2 plus 2 is 4, and so 4 mod 4 is 0. And so then this would be the 1 plus here. Okay. And so this is what it looks like. 3 plus 2 is 5, that's 1. 3 plus 3 is 6, that's 2. Okay. Now you may be saying to yourself, this is still kind of weird and abstract. Well, this is the reason. One of the reasons I like this example is because if you consider the Cayley table for just z mod 4, okay, remember z4 is what? 0, 1, 2, and 3. Right, so 0, 1, 2, 3, 0, 1, 2, 3. What's going to happen here? Well, you get 0, 1, 2, 3. And 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, which is 0 mod 4. And then 2, 3, 0, 1. Right? 2 plus 3 is 5, mod 4 is 1. And then 3, 0, 1, and 2. Now, what's really remarkable here is that these two multiplication tables are exactly the same. Right? Here's your 0 element, 0, 0, 0, 0, 0, 0, 0, 0. Here's your 1 element, 1, 1, 1, 1. Right, and you can see the 2's, everything's in the same position. What does that mean when you see something like that? When you've got two Cayley tables that are identical, and the groups have the same order and everything, right? It means that you're dealing with an isomorphism here. So obviously, or hopefully, so obviously z mod z4 is isomorphic to z4. Sorry. Z mod 4z, that's a different thing. This is isomorphic to z4. And we just saw that because we built the table, and we can see that they have the exact same structure. Now, in general, for n greater than 0, if we let nz equal 0, comma, plus or minus n, plus or minus 2n, plus or minus 3n, etc., etc., then z mod nz is going to be isomorphic to zn. Right? That's an interesting result, and you could check it. Right, we just did it for 4. We'll try it for 6 or 8 or something, or a random number, whatever you like. Right, so this is an example of the factor group z and z. So this would be z 4z that we just looked at. Okay, let's do another example. Right, so you can see the tremendous structure of group theory starting to really emerge. Like, my goodness, it's layers and layers of structure on top of structure on top of structure. Right, when you start with a simple idea of a group, you get all this structure. Let's take a look at another example. Okay, so let's let, in this case, let's let G equal Z18, so the integer is mod 18. And let's let our H subgroup, normal subgroup, be the group generated by the integer, or the element 6 in Z18. So that's going to be what? Well, 0, 6, 12, plus 6 more is 18, which is 0. Right, so there's your normal subgroup. Right, so 0, 6, 12 is a normal subgroup of G. Right, so we'll say it like this. 6 is a normal subgroup of Z18. Okay. And It turns out that we can easily enumerate, we can easily write out Z18 factor group with this 6. So this G mod H, or the Z18 mod cyclic group generated by 6. Turns out it's equal to 0 plus H, 1 plus H, 2 plus H, 3 plus H, 4 plus H, 5 plus H. And how do the elements combine here? So how do the elements combine in these examples? So if I have 5 plus H and I want to combine it with 4 plus H, well, this operation is kind of addition operation. Right? So I get 5 plus 4 plus H, so that gives me 9 plus H. And you can express this better in terms of the elements, right? So this would be equal to 3 plus 6 plus H. And of course this is just 3 plus H, right? Since 6 is absorbed by the subgroup, right? 6 is in H, and so it's going to be absorbed. Okay. Right, so H is going to absorb all multiples of 6. That's the nature of H. Right, and so this is the factor group Z18 mod 6. Okay. All right. Very good. Let's end the video here. When we come back, I want to do a longer example. We're gonna take a lot of time, and we're really going to break down a very critical physical example using dihedral group. So I'm going to end the video here just in the interest of not making the upload too significant. So we'll be back in a moment with part B.